Hello, today I got an IPM for power semiconductors, so I will explain how it works while using it. Here is the IPM. Inside this small package there are multiple power semiconductors and everything needed for driving them. It's an intelligent power module IPM. I will explain the details later, but it contains circuits shown here. An inverter and its driver circuit. If we design an inverter without an IPM, we need separate power modules and driver circuits like these. But with an IPM, most of the peripheral circuitry is already integrated, so building an inverter becomes much simpler. Today I'm going to build an inverter using an IPM and use it to drive a motor. This will give us a good idea of how easy an IPM is to use in a real-world application. First, I will explain where IPMs are actually used. They are mainly used in inverter circuits. This section is the main circuit of the inverter. It consists of 6 power semiconductors. The main inverter circuit may be built using discrete power semiconductors like this one, or it may be built using standard non-intelligent power modules like this one. The package and the components can vary quite a lot, depending on the application. And this IPM is a device where the main inverter circuit and the gate drive circuit are integrated. Once the inverter's main circuit is connected to the motor and some voltage is applied, the motor begins to rotate. Inverters using IPMs are commonly found in household appliances such as air conditioners, refrigerators, and washing machines. In air conditioners, IPMs are used in the inverter that drives the outdoor fan motor and the compressor motor. In washing machines, IPMs are used in the inverter that drives the motor that rotates the washing drum. In general, IPMs are commonly used in applications where motors are driven. From here, I'd like to take a closer look at what's inside the IPM, but before that, let's talk a little bit about its appearance. In fact, there are various types of IPMs available in different package styles. In this video, I'm using this small IPM from Fuji Electric, the P633A series. It looks like an IC and it's relatively small for an IPM. Because of that, the amount of power it can handle is also limited. It's rated for 650 volts and 10 amps, making it suitable for use in household air conditioner compressor motors. On the Fuji Electric website, you can also find standard IPMs. This type of IPM package is commonly used in applications that require a bit more power. For example, commercial air conditioners, industrial inverters, and so on. They come in different packages, but as IPMs, their roles and functions are the same. Next, let's take a closer look inside the IPM. This diagram shows the internal structure of the IPM. This is the package I've shown a few times already, and this circuit is inside it. These here are the power semiconductors in the IPM. The IPM we're using today uses IGBTs. On the left-hand side, there are drive circuits for the IGBTs. This means that the power semiconductors can be driven without the need for an external IGBT drive circuit. In the actual application, the input signal will be fed from these points. You can directly input the control signals from the microcontroller to the IPM. Additionally, most IPMs have protection circuits built into the drive circuitry. If an overcurrent condition occurs, these circuits will immediately cut off the current to prevent damage to the IPM. However, in practice, an external circuit is required to detect the current. Without an IPM, when you use power modules or discrete devices, you have to design and implement all of those peripheral circuits yourself. With an IPM, it's all included from the beginning. This is a major advantage for anyone designing inverters, because it greatly reduces the amount of peripheral circuitry required to properly drive and protect the power semiconductors. This reduces the overall design workload and simplifies the circuit. These are the key advantages of using an IPM. So far, we've looked at what's inside an IPM. Next, let's compare regular power semiconductors with IPMs. Most power semiconductors you see are discrete types, like this one. In terms of circuitry, a discrete semiconductor contains only a single power semiconductor, either an IGBT or a MOSFET. In order to use discrete power semiconductors like this, you need to prepare a separate circuit to drive them. You need one drive circuit for each discrete power semiconductor. Another type is this power module. In fact, IPMs are classified as power modules. However, the power module I'm referring to here is a non-intelligent one. Typically, a power module comes in a package like this. Inside the package, multiple power semiconductors are integrated and connected in a configuration designed for specific applications. For example, this power module is called a 2-in-1 module, and the circuit looks like this. This switch here represents an IGBT. If you use just one of these, you can build a chopper circuit like this. If you use 2 of them, you can build a single-phase inverter. If you use 3 of them, you can build a 3-phase inverter. However, you don't actually need 3 2-in-1 modules to do this. There's also a package called a 6-in-1 module, where 6 power semiconductors are already connected internally to form a 3-phase inverter. However, this power module also requires a separate drive circuit for driving the power semiconductors, just like discrete power semiconductors. In a previous video, I built a 3-phase inverter using 3 power modules. I also built the drive circuit for the inverter, but as you can see, the overall circuit became quite large, and it was also somewhat expensive. So one of the key advantages of an IPM is that it has built-in drive circuits, which makes it easy to use. So far, IPMs might look like they have a lot of advantages, but there are some downsides as well. One of them is that they're not as flexible as discrete power semiconductors or conventional power modules. For example, with discrete power semiconductors, you can increase the voltage rating or current capacity by connecting devices in series or in parallel. With IPMs, however, this is basically not possible. Since each IPM has its own drive and protection circuits built in, there can be timing differences during switching or protection events. As a result, the current or voltage may become unevenly distributed and concentrate in a single IPM, which can eventually lead to device failure. For this reason, we don't connect IPMs in series or in parallel. Instead, we choose an IPM from the lineup offered by different manufacturers based on the application. Also, it is generally not possible to change the characteristics of the drive circuit inside an IPM. Therefore, fine-tuning by adjusting the switching speed, which is possible with discrete power semiconductors or conventional power modules, is not possible with IPMs. Even though IPMs have these kinds of drawbacks, the benefits outweigh the disadvantages, which is why IPMs are still widely used in many applications today. I actually created a three-phase inverter using an IPM. This is the circuit I made. The IPM is mounted on the back. Basically, I built it almost exactly according to the datasheet and application note. The layout and wiring are almost the same as the application note. This one is quite different from the three-phase inverter I made before, both in terms of specs and components, so it's hard to compare them directly. But overall, I managed to make it pretty compact. The IPM I'm using can accept control signals directly from the microcontroller without requiring any level conversion. I designed the inverter to take advantage of this feature. If you want to protect the microcontroller in case the IPM fails, it's a good idea to use optocouplers in these parts to isolate the signals. In the actual application, there's a heat dissipation surface here on the IPM, as you can see, so this part should be in contact with the heatsink to dissipate heat. Now, let's actually use this IPM-based three-phase inverter to drive a motor. This controller connected to the IPM is the same one I used when I built the KQ do re mi fa inverter before. The DC supply is set to 200 volts this time. A shock at 200 volts DC would be no joke, so I'm wearing these insulated gloves and trying to be a bit more cautious than usual. Now let's get started. Power on. For now, nothing's happening. If I keep turning this, it's working for now. So let's properly run the inverter. It's working perfectly, looking good. Since the voltage went over 100 volts, I started feeling pretty nervous while running the inverter. When I was controlling the do re mi fa inverter, the motor made a tulululu sound during acceleration. But modern trains no longer make such distinctive sounds when accelerating or decelerating. The reason for this is that the inverter is controlled to reduce noise. Specifically, this is done by increasing the switching frequency from several kilohertz to over 10 kilohertz. Actually, with this IPM-based inverter, you can also reduce motor noise by adjusting the control settings on this controller. Let me try it. It's actually pretty simple. You just need to change the code on this controller. Therefore, the trains and Shinkansen that are currently in operation can actually produce musical sounds like a do re mi fa inverter, simply by changing the program. But of course, they don't actually do that. So I'll run the inverter the same way as before. Power on, and then I turn this dial here. It sounds totally different from earlier. You might be hearing a faint high-pitched ringing sound. So this is the sound. It might sound a little harsh here, but in real railway operations, this harshness is reduced to produce more pleasant sound. Also in household appliances like air conditioners, washing machines, and refrigerators, the inverter's switching frequency is adjusted so the switching noise is outside the range of human hearing. So today I went over IPM, including its basics, internal structure, and how it compares to conventional power semiconductors and power modules. I also built an inverter circuit using an IPM and actually used it to drive a motor. An IPM integrates power semiconductors, drive circuits, and protection circuits into a single module, making it easy and convenient to build an inverter. While IPMs may not offer quite as much flexibility as discrete power semiconductors or conventional power modules, their simplicity and convenience more than compensate for this limitation, which is why they're such a popular choice for a wide range of household and industrial applications. I built a three-phase inverter with an IPM myself, and by doing so, I was able to greatly reduce the number of components and make the entire circuit much smaller and more compact. IPMs are really convenient modules, so I definitely recommend thinking about using one if you're planning to build an inverter. Thank you for watching. See you next time.